Hi, it's Mr. Anderson, and today I'm going to be talking about physics. Physics comes from a Greek word, physis, which just means nature. And so you could argue that physics is the oldest science that we have, because the first time somebody looked up at the moon and wondered why the moon goes through its phases, they were doing physics. And so it's been around thousands of years, but it really didn't become quantified until we got to the scientific revolution. One of the big names is Galileo Galilei. Again, he really was good at using the telescope and made some amazing discoveries as far as space. But he also did some studies in mechanics or in kinematics, or how objects move. He probably didn't drop those objects from the Leaning Tower of Pisa, but he did do some cool experiments on pendulums. And so let me show you an example of what he did. I'm using software called Fun. Fun is a physics simulator, and it actually is a lot of fun. What you can do is build objects, and then you just hit play, and then those objects will start to move. And so that's a simple pendulum, one similar to what Galileo was actually studying. And so let me move back for a second, and let me make another pendulum over here. And one of the first things he discovered is that when you had two pendulums, we'll say the one on the left and one on the right, and the one on the right has a longer length, that one's actually going to have a longer period. In other words, the time it takes to swing back and forth. He also found that no matter what the object's weight is, they had the same pendulum. And so he was starting to figure out this idea, at least that all objects seem to swing, if not fall, at the same rate. So let me get rid of some of these and clear this off. And now we'll go back and talk a little bit about the next scientist, and his name was Isaac Newton. Isaac Newton came up with three theories, or three laws, and you've probably learned these before. First one is the idea of inertia, and you've maybe heard it this way, that an object at rest tends to stay at rest, an object in motion tends to stay in motion, so we call that his first law. His second law could be summarized as this: force equals mass times acceleration. And then the last one is this idea that for every action there's an opposite and equal reaction. And so we call those reaction pairs, is a good way to say that as I make that. In other words, when I push on a wall is pushing back equally on me. And so let's jump into the virtual world and take a look at how those would work. First of all, let me add a ground for just a second. And so now I'm going to add, let's go back actually. So let's add a ground, and now let me add an object. And so let me rewind for just a second. So if I add a ball like this and hit play, that object is going to fall like that. If I rewind it for a second and I lose gravity, so there's no gravity and I hit play, what's going to happen? Well, if there's no gravity and I hit play, that object is now at rest, and so it's going to stay at rest. Once I add gravity to it, it's just going to fall. Now if I time it right, again, I had it bounce, and then I got rid of gravity, and it just kept going in that direction. If I add gravity again, it's just going to fall all the way down. And so that's Newton's first law. An object in motion stays in motion, an object at rest is going to stay at rest. And if you're paying attention down here, this object is starting to move up because I've got rid of gravity, so we can make it stick down to the bottom. Okay, what was Newton's second law? Newton's second law, remember, is that force is equal to mass times acceleration. What does that mean, F equals ma? Well, it essentially means that if you apply a force to a small mass, you're going to get a huge acceleration. Or if you apply a force to a huge mass, you're going to get a small acceleration. So let me give you an example of that. Let's bring in a catapult. And so if I bring a catapult in like this and hit play, catapult's going to throw that object. Oops, I got rid of gravity for a moment. So if it's going to throw that object in the other direction, like that. Let me rewind that for a second. And so what I can do is I could grab this little object right here, and I can change what it's made up of. And so let's change its mass. And so now let's not have it be a mass of 60 grams. Let's make its mass be much bigger, like 1.5 kilograms. So if I throw it again, it's not able to throw it. So what again I've done is I've increased its mass, and so its acceleration got slower. Well, let's try and find something in the middle. Let's find a mass that maybe works. So something like that. And so that would be Newton's second law. In other words, as you increase the mass of an object, that object is going to, its acceleration is going to drop off. Now, one thing you should have seen when we did that is, don't take a look at the object this time, but let's take a look at the catapult. What happens when it, did you see that? So when the object goes to the right, in this case, then the catapult goes in the left. And so that's Newton's third law of motion. For every action, there's an opposite and equal reaction. Now, why did the object go farther than the catapult? That goes back to Newton's second law. Well, I'm getting into a lot of physics, and physics that we'll actually deal with later. But the reason I'm doing all of that is that I want you to understand that physics, once we started quantifying it and we came up with these laws, it never changed. In other words, for the next 200 years, once we had Newton's laws of physics, that was it. And in fact, in our book, the physics that we cover is just Newtonian physics. And so what do I mean by that? Well, mechanics, so we're just talking about one specific type or one part of physics. Mechanics, and all we understood about mechanics, dealt with just this box down here. And so if we look at the size of objects, and so right here I'm going from size of objects down at the level of an atom, so this would be an atom down here, up to the size of a planet up here. So if we go from the very small to the very big, classical mechanics or Newtonian physics only works if you're dealing with big objects, like objects the size of me, or the objects the size of a catapult. But when you get down to the level of an atom, it really didn't make sense. Speed is another thing. So if we go from speed where we're not moving, or moving as fast as a bicycle, and then we move up to the speed of light, the rules tend to change as well. And so physics is a really broad science. But we didn't start to understand this until we started to get some people. And so Einstein was the first person to start to explain what happens to objects, not just swinging on a pendulum, but as they start to move really fast and as they move towards the speed of light. And he found some really crazy stuff. Like as you start to approach the speed of light, time will actually slow down for you. In other words, you could travel away from here at the speed of light and come back, and you and I are going to be a different age. We also had, this would be Max Planck, but a lot of scientists came up with this idea of quantum mechanics. Quantum mechanics is kind of explaining what happens at that atomic level, where we start to get this duality, where it's not only a particle, these small little objects, but they have properties of waves as well. And then finally, we have this, in this last century, the arrival of what's called quantum field theory. Again, I could put tons of scientists with each of these, but this is Richard Feynman, who actually is, it's just fascinating. If you want to be fascinated by a scientist, type that into YouTube and you're going to find some wonderful interviews. But he came up with these Feynman diagrams to explain what's going to happen, not only at high speed, but at the atomic level. And so what I want you to understand is that classical mechanics or Newtonian physics is really what we're going to talk about for a lot of the year in physics, but it's just one thin slice of the pie that is physics. And even with that, mechanics is one thin slice of physics. So we're going to deal a lot with kinematics like acceleration, motion, graphing. But there's a whole other group of physics in physics called thermodynamics, where we deal with things like heat. There's another group where we deal with electromagnetism. So we deal with things like electricity and magnetism and light and optics. And so I'm leaving some things off here. Physics also is made up of a lot of the idea of this quantum theory and how we move at that small level. And so there's a lot to physics. But what I want you to understand is that physics is simply a way to understand our world. And if you understand that, you've taken a first step.